Right now, as you are watching this video, there is a machine built by human hands that is so far away from you that if you screamed at it and your voice somehow traveled at the speed of light, the fastest speed anything can travel in this entire universe, it would still take almost a full day to reach it. Not a few seconds, not a few minutes. Almost 24 hours, one way, just to cross the distance between you and this spacecraft. And here's the part that should genuinely unsettle you. In November 2026, just months from now, that number is going to tip over into something that has never happened in the history of our species. A human-made object is going to become the first one ever to sit a full light day away from Earth. A distance so absurd that NASA itself has to explain it in stages just to make it comprehensible. We are talking about Voyager 1. And the terrifying question underneath all of this, the one almost nobody stops to actually sit with, is this. This spacecraft is now so far away, so faint, so old, that every single year it slips further past the edge of what we can reliably track, communicate with, or ever hope to physically retrieve. And one day, without warning, the signal is simply going to stop coming back, and we may not even know exactly when it happened or exactly where it was, when it finally went silent forever. So where, precisely, is humanity's farthest spacecraft right now? How did it get impossibly far out there? And what happens to it after we lose it for good? To understand how far 15 billion and soon 16 billion miles actually is, you have to start at the beginning, because Voyager 1 did not launch with the goal of becoming humanity's most distant object. It launched on September 5th, 1977 from Cape Canaveral, Florida, just over 2 weeks after its twin, Voyager 2, even though Voyager 1 would go on to overtake its sibling and become the faster, farther traveling of the pair. Both spacecraft were built to take advantage of an extraordinarily rare planetary alignment that occurs only once every 176 years. One that let a single spacecraft use the gravity of one giant planet to slingshot itself toward the next. A maneuver engineers call a gravity assist, essentially stealing a tiny sliver of a planet's own orbital momentum to accelerate for free. Voyager 1 flew past Jupiter in March 1979, sending back images that stunned scientists, including the first ever confirmed evidence of active volcanoes anywhere beyond Earth, erupting on Jupiter's moon Io. It then swung past Saturn in November 1980, using Saturn's own gravity for one final deliberate slingshot, a maneuver that boosted Voyager 1's speed dramatically, but came at a cost, permanently bending its trajectory up and out of the flat plane in which all the planets orbit the Sun, meaning Voyager 1 would never again fly close to another planet in our solar system. That single decision, made by mission planners in the late 1970s, is the exact reason Voyager 1 is now the faster of the two probes and holds the record for distance, while Voyager 2 took a slower, more scenic route past Uranus and Neptune and now trails behind. After Saturn, its primary mission technically complete, Voyager 1 simply kept flying, and it has not stopped since. It crossed the orbit of Pluto. It kept going past the point where the sun's light became a faint pinprick rather than a source of daytime warmth. And on August 25th, 2012, it reached a boundary that no human-made object had ever crossed before, called the heliopause, the outer edge of the heliosphere, which is the enormous bubble of solar wind and magnetic fields that our sun blows outward in every direction, acting almost like an invisible force field around our entire solar system. Crossing that boundary meant Voyager 1 had officially left the direct influence of our sun's particles and entered true interstellar space, the actual material and radiation that fills the gaps between star systems. NASA did not announce this milestone immediately, spending months afterward carefully analyzing the plasma density data streaming back from the spacecraft's instruments to be absolutely certain the numbers matched what interstellar space should look like, before confirming it publicly in September 2013. Voyager 1 remains, to this day, one of only two spacecraft that has ever accomplished this. Its twin Voyager 2 followed it out through the heliopause 6 years later, in November 2018, but along a completely different trajectory and reaching that boundary at a different point in space entirely, because the two probes have been flying in almost opposite general directions since they left Saturn behind. So where exactly is Voyager 1 sitting in space right now, at this very moment? As of the middle of 2026, Voyager 1 is more than 25 billion kilometers from Earth, somewhere north of 15 billion, 700 million miles away, which works out to roughly 170 astronomical units, with one astronomical unit being defined as the average distance between the Earth and the Sun. To put that in a way that actually means something, Voyager 1 is currently over 5 times farther from the Sun than Neptune, the most distant official planet in our solar system, and it did not stop moving for a single second to get there. It is still traveling outward at roughly 17 kilometers per second, or about 38,000 miles per hour, fast enough to cross the entire continental United States in under 3 minutes, and it adds something like 3.5 astronomical units, more than 500 million kilometers, to its distance from Earth every single year, a number that will keep climbing for as long as the spacecraft keeps functioning and quite a bit longer after that. Because of this staggering distance, a radio command sent from one of NASA's giant deep space network antennas right now takes close to 23.5 hours just to physically arrive at Voyager 1, and then another 23.5 hours for any reply to make its way back, meaning a single question and answer exchange with humanity's farthest spacecraft currently costs the better part of 2 full days, every single time. And that number is about to cross a threshold that has never existed before in the history of spaceflight. NASA has calculated that on November 18, 2026, at 2:16 in the morning Pacific time, Voyager 1 will be exactly 16,094,799th or 96 miles from Earth, or 25,902,000 or 68,856 kilometers, a distance so precisely calculated it almost feels absurd next to how genuinely enormous it is. And that distance happens to be exactly what astronomers call one light day. The distance that light itself, moving at 186,000 miles every single second, travels across in a full 24-hour period. Voyager 1 will become the very first human-made object in history to sit a full light day away from the planet that built it. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has compared reaching farther and farther distances to wading further out from the shore into open water, where the ripples, waves, and currents around you keep changing the farther out you go, and at some point, conditions start to stabilize into something new entirely. And that is essentially what Voyager's remaining instruments are still trying to measure, mapping out exactly how the interactions between our sun's fading influence and true interstellar space change as the spacecraft continues its outward crawl. Here is where the story gets a little bit eerie, though, because being this far away does not just mean a long wait for a signal. It means the spacecraft itself is now operating in a kind of permanent twilight, running on borrowed time in almost every conceivable sense. Voyager 1 gets its electricity from a radioisotope thermoelectric generator, a device that produces power from the natural, unstoppable radioactive decay of plutonium. That decay never pauses, never resets, and can never be topped up or refueled from Earth. Every single year, without exception, Voyager 1 permanently loses about 4 watts of available power, a number that sounds small until you realize the spacecraft's total power budget was never enormous to begin with. And after nearly 50 years, engineers have been forced into a long, quiet process of shutting down instrument after instrument, heater after heater, essentially trimming away pieces of the spacecraft's remaining capability just to keep its most essential systems, its ability to orient itself, and its ability to talk to Earth at all, alive for a little bit longer. Out of the 10 scientific instruments Voyager 1 originally carried when it launched in 1977, only a small handful still function today, with NASA and mission scientists estimating that current power trends put the spacecraft on track to lose the ability to run any of its instruments at all sometime in the early 2030s, at which point the mission would likely be declared complete, not because Voyager 1 stopped moving, but because it will have finally run out of the electricity needed to keep listening and speaking to us at all. What is genuinely remarkable and slightly haunting when you sit with it is who is actually running this mission at this point in its life. Dodd has described the Voyager team today as a strange and moving mix of generations. Veteran NASA engineers now in their 80s, some of them technically retired, who still get called back in as consultants because they are quite literally among the only people alive who remember the specific quirks of hardware and software systems designed and built in the 1970s, working shoulder to shoulder with brand new engineers, so young that their own parents had not even been born yet when Voyager 1 first launched off the pad in Florida. That intergenerational relay race, handing this fragile, irreplaceable machine carefully down through nearly 50 years and multiple generations of engineers who were never even alive to meet each other in the mission's early years, is part of what makes the Voyager program feel less like ordinary engineering and more like a kind of sacred inheritance being passed hand to hand across time, keeping one very old, very tired, but very determined machine breathing for just a little bit longer. It also helps to understand exactly how Voyager 1 stacks up against every other spacecraft humanity has ever sent outward. Because the gap is not small, it is almost absurd. Its twin, Voyager 2, launched slightly earlier but took the longer, more scenic route through the outer solar system, flying past Uranus in 1986 and Neptune in 1989, becoming the only spacecraft in history to have visited all 4 of the solar system's giant planets. The detour cost Voyager 2 speed and distance, and today it trails behind its sibling by a significant margin, currently sitting at roughly 19.5 light hours from Earth, compared to Voyager 1's nearly 23.5 light hours, meaning Voyager 1 is pulling farther and farther ahead of its own twin with every year that passes. Beyond the 2 Voyagers, NASA also launched a pair of earlier probes, Pioneer 10 and Pioneer 11, in the early 1970s. which were technically the first spacecraft ever to travel through the asteroid belt and past Jupiter and Saturn, and which also carry their own small golden plaques with symbolic messages for whatever might one day find them. But both Pioneer probes lost power decades ago. Pioneer 10's last confirmed signal arrived in 2003, and Pioneer 11's even earlier in 1995. Meaning both of them are still out there, physically intact, still moving, but completely and permanently silent, unreachable, essentially lost forever the moment their radioisotope power finally dropped below the threshold needed to run a transmitter. In a strange way, watching Voyager 1 approach its own inevitable silence is a little bit like watching a slower motion replay of exactly what already happened to the Pioneer probes. A fate the Voyager team knows, with total certainty, cannot ultimately be avoided, only delayed. There's also New Horizons, the spacecraft NASA sent to Pluto in 2006, which flew past the dwarf planet in 2015 and continues onward into the distant, icy region beyond called the Kuiper Belt. But even after all these years, New Horizons remains only a small fraction of the distance Voyager 1 has already covered, still comfortably inside the outer edges of the solar system's debris field, nowhere close to the heliopause, let alone true interstellar space. It is a useful reminder of just how much of a head start Voyager 1 really has, and how unlikely it is that any spacecraft launched within our lifetimes will ever catch up to it, because newer missions are generally built for specific, targeted science goals rather than raw, brute force distance, meaning Voyager 1's record as the farthest human-made object in existence is likely to remain unbroken for a very long time, possibly for the rest of this century, unless some future mission is deliberately designed from the ground up purely to outrun it. Staying in contact with something this far away also depends entirely on a small, incredibly specialized set of giant dish antennas scattered around the planet, collectively known as the Deep Space Network, with major complexes located in Goldstone, California, Madrid, Spain, and Canberra, Australia, spaced roughly 120 degrees apart around the globe so that, as the Earth rotates, at least one of them can always keep a dish pointed toward deep space at any given moment. Reaching Voyager 1 specifically requires the network's largest antennas, enormous 70-meter-wide dishes, because the signal coming back from the spacecraft by the time it crosses 25 billion kilometers of empty space has become almost unimaginably faint, arriving at a strength some engineers have compared to trying to detect a refrigerator, light bulbs worth of power spread out across a distance measured in billions of miles. When the Canberra antenna went offline for a period of scheduled upgrades, it created a genuine logistical crisis for the mission because it happens to be the only dish reliably positioned to communicate with Voyager 1 during certain parts of Earth's rotation, and losing access to it, even temporarily, meant losing entire windows of opportunity to send commands or receive data from the spacecraft at all. It is a strange, humbling thought that an entire spacecraft's fate at any given moment can hinge not just on its own aging hardware 15 billion miles away, but on routine maintenance schedules for enormous radio dishes sitting quietly in the Australian outback. Because even after it eventually goes silent for good, it is not simply going to stop or drift to a halt somewhere out in the dark. There's essentially no friction in interstellar space to slow it down, no atmosphere to burn it up, nothing dense enough out there to meaningfully collide with across the almost incomprehensible emptiness between stars. So Voyager 1 will simply keep traveling in a straight line, forever, completely unpowered, completely silent, carrying its cargo through the galaxy, long after every trace of its mission control has vanished from the face of the Earth. Scientists have actually mapped out its rough future trajectory, and in roughly 40,000 years from now, an almost unimaginable span of time, Voyager 1 is projected to drift within about a light year and a half of a star called Gliese 445, a small red dwarf star sitting in the constellation Camelopardalis, not close enough to be considered any kind of true visit or flyby in the way we usually imagine spacecraft encountering planets, but close enough in the almost unfathomable emptiness of the galaxy to briefly count as something like a near neighbor for a fleeting moment in cosmic time. To put that same kind of scale into perspective a different way, Proxima Centauri, the single nearest star system to our own sun, sits about 4 light years away from Earth. And even traveling at Voyager 1's current blistering speed of over 38,000 miles per hour, it would still take the spacecraft something in the neighborhood of 73,000 years just to cover that comparatively short cosmic distance if it happened to be heading in that direction at all, which it is not. Voyager 1 is not, in any meaningful sense, going anywhere in particular. It is simply going outward, endlessly, into the vast, mostly empty space between the stars of our galaxy. This is exactly why the golden record riding along on Voyager 1's hull matters so much to the story of where this spacecraft actually is and where it is actually going. Carl Sagan and a small team of scientists assembled a physical, analog phonograph record before launch, gold-plated and sealed in an aluminum jacket, etched with symbolic instructions on how to play it, and packed with greetings recorded in 55 different human languages, natural sounds from Earth like thunder, wind, and animal calls, 90 minutes of music spanning cultures and centuries, and even a recording of a human heartbeat. It exists on the extraordinarily remote chance that someday, somewhere out in that same vast darkness Voyager 1 is now drifting through, something might find it. Sagan himself was deeply aware of just how staggeringly unlikely that is, and he was also the one who, in 1990, had Voyager 1's own cameras turned back around toward Earth from nearly 4 billion miles away, capturing a single, almost imperceptible, pale blue pixel of light, suspended in a stray beam of sunlight, an image that became known as the pale blue dot, and which Sagan later described in words that still circulate widely today, about how that tiny point of light was the only home we have ever known, everyone we love, everyone we have ever heard of, every human being who has ever lived, all of it, on that one fragile pixel captured by a camera that was already, even in 1990, unimaginably far from home and only getting farther every single day since. Understanding exactly where Voyager 1 is right now also means understanding a strange kind of numerical fog that surrounds its location. Because unlike a car with GPS or a ship with a transponder pinging its coordinates constantly, Voyager 1's actual position at any given second is not something anyone can simply look up instantly and know for certain. It has to be calculated continuously, using the spacecraft's known velocity, its trajectory since the last confirmed contact, and the timing of its faint, whisper-quiet radio signal as it arrives back at Earth's deep space network antennas in California, Spain, and Australia. NASA maintains live tracking tools, including an interactive visualization system called Eyes on the Solar System, specifically because the distances involved are so enormous and so constantly increasing that a static number would be outdated within moments. And even these tracking tools are working from a signal that, by the time you actually read it on a screen, already describes where Voyager 1 was over a full day earlier, not where it actually is, at the literal instant you're looking at the number. In a very real sense, nobody on Earth has ever truly known where Voyager 1 is right now, only where it recently was, and by the time any of us finds out anything new about it, the spacecraft has already moved on, farther still, deeper into the dark, always just slightly ahead of our ability to actually catch up with the truth of its position in real time. To really feel the scale of where Voyager 1 currently sits, it helps to shrink the entire solar system down to something more human-sized for a moment. If the sun were the size of a basketball, Earth would be a tiny grain of sand sitting about 26 meters away. And on that same scale, Voyager 1 right now would be roughly 2.5 kilometers away from that basketball, drifting steadily farther with every passing second, having already covered a distance on that model equivalent to walking from one side of a small town to the other, and still going with no destination, no finish line, and no planet or star anywhere along its current path that it is actually aiming for. Another way to picture it is through pure travel time using speeds we experience every day. A commercial airplane cruising at around 500 miles per hour would take more than 3,500 years just to cover the distance Voyager 1 has already put between itself and Earth. And by the time that imaginary airplane finally arrived, Voyager 1 itself would already be more than 70 billion kilometers farther out still, because it never stops moving, never needs to refuel in the way an airplane does, and simply coasts onward under nothing but the momentum it picked up from Jupiter and Saturn's gravity nearly 50 years ago. That single ancient assist from 2 planets is still doing all the work today, carrying humanity's farthest emissary outward every single second of every single day, long after the engineers who calculated that trajectory in the 1970s have mostly retired, and in some cases passed away without ever knowing exactly how far their small, careful piece of math would ultimately carry this remarkable little spacecraft into the dark, that so many people watching videos like this one eventually ask, which is simply, when do we actually lose Voyager 1 for good, and will we even know when it happens? The honest answer is more unsettling than most people expect, because there likely will not be one single dramatic final moment. No last words, no countdown, no clean goodbye. Instead, mission engineers expect a slow, almost graceful fade. One final instrument switching off, one last heater going cold, one final watt of power draining away from a radioactive power source that has been quietly decaying since before most of the people reading this were even born, until eventually a scheduled contact attempt from the Deep Space Network simply returns nothing at all. No data, no telemetry, not even the faint carrier signal that has reassured engineers for decades that Voyager 1 was still out there, still listening, still willing to answer if we called. And even then, there's a real chance NASA will attempt contact again anyway, on the off chance that the failure was temporary. A corrupted computer, a mispointed antenna, a power dip triggering a fault protection shutdown, the same kinds of glitches this exact spacecraft has already survived more than once across its remarkable, improbable, nearly 50-year lifespan. Nobody currently working on the Voyager mission wants to be the person who declares it dead prematurely, because this spacecraft has already defied realistic expectations so many times that a small, quiet part of the team seems to hold out hope. It might somehow keep answering long after everyone reasonably expected it to have gone silent. But eventually, statistically, physically, it will happen. The power really will run out completely, and Voyager 1 will become nothing more than a silent, drifting artifact. A fully intact, functioning piece of American engineering from the 1970s, tumbling gently through the emptiness between the stars, its transmitter dead, its instruments dark, its golden record sealed shut and utterly unreachable by anyone, unless, in some distant future, measured not in decades but in tens of thousands of years, some other intelligence, somewhere out there in that same vast darkness, happens to notice a strange, tiny metallic object drifting past and decides to take a closer look. Until that day, right now, this very second, Voyager 1 continues to sail outward through interstellar space at more than 17 kilometers every single second, more than 25 billion kilometers from the planet that built it, still occasionally answering when we call, still against every reasonable expectation anyone had for it back in 1977, somehow, impossibly, still out there and still listening.